Okay, so this week we're going to move forward with more hypothesis tests, more confidence intervals, all of this stuff. This time we're going to be working in Chapter 9. But before I move on, I want to make sure that all the stuff we covered from Chapter 8 is okay, especially regarding I guess 2 sample hypothesis tests for proportions. Sorry. Did the homework go okay for Chapter 8?
It was kind of.
Okay. Yeah. These last 2 chapters are really where it gets tough, and really where basically everything we've done up to this point has been building up to these last 2 chapters, and probably the final exam will look most similar to these last 2 chapters. Okay, so chapter 8 and chapter 9. So yeah, so this week we're covering chapter 9. Next week we'll just touch on chapter 12, very lightweight, and we'll start reviewing chapter 8, chapter 9 stuff, and then the following week is all going to be review. So.
Wait, we're doing only 8 and 9, or 8, 9, and 12?
We are doing 8, 9, and 12, but chapter 12 is very lightweight. Okay, it's just a few definitions and just a few concepts there. Yes.
Isn't the next quiz on Tuesday?
Yeah, next Tuesday you've got a quiz covering chapters 8 and 9. Yeah. So. Okay. All right. Okay. Well, we'll try a sample problem. This will be 2 sample proportion. Okay, so this is just kind of a review. So if we have, let's say the problem reads something like this, okay? We wish to know if a new medication is more effective in treating cold symptoms than the old medication. Okay, so we randomly assign 600 people to different treatments. Okay. 300 problem written out. Is everyone able to read this?
Yeah.
That's good. So we have 600 people, and we randomly assign them. 300 are given the new medication, and 180 show improvement in their symptoms. Okay, and 300 people are given the old medication, and 156 show improvement in their symptoms. Okay. So, does this mean that the new medication is more effective than the old medication? Okay, so this is a two-sample proportion hypothesis test. We saw problems like this in our homework, right? Okay. So why don't I give you guys a few minutes to work on this, get as far as you can. All right. I guess I'll structure maybe how your answers should go, which should help you along the way. So first, come up with the hypotheses. Okay. Figure out your observed difference. Observed difference between proportions. Calculate your standard error. Find a z-score. Get your p-value. And make a conclusion. Okay, so this is all review from last week.
Professor?
Yes.
Will last week's lecture be posted online?
Yes, I apologize for the
Okay.
delay in getting it posted. So.
The lecture's supposed to be online.
Oh.
whoever gets the correct p-value, okay, first. Okay, so we see. Huh? Yeah, so whoever gets the correct p-value first, we'll give some bonus points on their I don't know, homework or something. Okay. And if anybody can beat me, I'll give you 10. So I'm gonna get plus 10. I'll get started right now.
I think I did something wrong.
Okay, I got my answer. Okay, you got it? You got it?
0.0239.
Oh, okay, that's good. What would you get? I'm sorry? All right, what'd you get? What? Okay. Hey, what did you say?
0.0239.
0239. Okay, and what did you say over there? 1029? 0029? Alright, Nona, you win. Alright. 0.0 I got 0.0244, but that's close enough. 0.0239. Okay.
Did you just guess?
No.
I don't think you can just guess this answer, alright? Yeah. Huh? Yeah, you were off by a factor of 10, so I can't give you. Huh? You said 0.0029? What did he say? Say that out louder. Okay, but it's not 0.029. This is 0.0244. Okay? Okay. Alright, so now I'll give you some points. Okay. Null hypothesis. Alright, what are we trying to do? We want to know if, what do we want to know? The question we want to know is, does this provide evidence that the new medication is more effective, right? So if the new medication is more effective, what would happen?
We would not have evidence to support the no.
Well, what should happen when people take the new medication over the old medication?
Better.
More people should get better under the new medication than the old medication. Is that happening when we look at our data?
Yes.
Yes, right? 300 people took the new medication and 180 improved. 300 people took the old medication and 156 improved, okay? So it seems like the new medication is more effective, okay? We want to know this difference between 156 and 180. Could that just be a result of just the fact that everybody's different? Things are random. Whenever you do a trial, sometimes more or sometimes less of something will happen, right? So we want to know, could this just be due to the randomness of life, okay? Or is this evidence that the medication is actually more effective? That's what we want to know, okay? So I'm going to create two hypotheses, the null and the alternative. What is the null hypothesis in words? The null hypothesis in words is that the two medications are the same, equally effective, okay? The two medications are equally effective. Alright, how do we measure how effective the medication is?
We give it to the patient?
No. With our data.
Oh.
How do we measure how effective are the medications. What are we calculating?
How many symptoms?
The proportions that improve. Okay? So in this case, if the two medications are equally effective, the two proportions should be the same, right? There should be no difference between the two proportions. So my null hypothesis is that P1 minus P2 is what?
0.
Equals to 0. Alright, and then the alternative, in words, what is it? It's not that the two medications are equally effective, it's that
The new medication is.
new medication is more effective, right? Alright, so symbolically, how do we write that?
P1 minus P2 is greater than 0.
That's correct. Okay. So P1 represents the proportion under the new medication, and P2 represents the proportion under the old medication. Yes?
Can we write the null hypothesis as P1 equals P2, or would you
Yes,
prefer to do
that's also
that way?
okay. Okay?
And
So
then for HA,
and
it'd be P1
you can
is
write
greater
P1
than
greater than P2. Okay? They're both saying the same thing, right? Okay, what is our observed difference between proportions? Okay, so over here I've got P's without hats, but over here I'm going to calculate P hats, right? So what is P1 hat? Yeah, it's going to be 180 over 300, 0.6. What's P2 hat?
0.52.
Okay, 156 over 300, 0.52. It's just cracking me up because you guys are talking in unison here. Okay, so our observed difference here is what? We have an 8 percentage point difference. Is this clear to everyone? I was walking around and I only saw a few people working, okay? So that's a little discouraging and disheartening as an instructor. Because I want you guys to try. Whenever I present problems for you to try and test your own knowledge, I want you guys to actually try. So you can see where you're making mistakes, where there might be a disconnect, okay? So we have 0.08 as our observed difference between proportions, okay? Huh? You got that?
I got that.
Okay, that's great, okay? So you're on the way. Alright, the standard error, again, is an ugly formula of which we can do nothing, okay? Or about which we can do nothing, okay? P hat times 1 minus P hat over times 1 over N1 plus 1 over N2. Okay, what is P hat? Yeah, P hat is our total success over total observed, right? Total success over total observed. So how many people improved symptoms? That's going to be our total success. If I do 180 plus 156 over 300 plus 300. So I get 336 over 600, which is equal to 0.56. Do we get this? Yeah, okay. So that means my standard error is going to be what? 0.56 times 1 minus 0.56 times 1 over 300 plus 1 over 300. Square root of the whole thing. And I get, alright, so check your calculators and make sure you can get this answer here. 0.04053. .04053. calculator.
Then you use the normal table to look at that value.
Okay, what do we have questions about? Here, do you have questions?
Confused on the S part, you don't, standard error part.
Yeah.
Okay, after you do 0.56, and then when you do 1 minus 0.56, you have 0.44.
Uh-huh.
And then after that, I'm lost.
Okay, so here I'll write this bigger so we can all see. All right, and I'll put in implied symbols here. Okay, so it's 0.56 times 1 minus 0.56. Okay, now whenever you see parentheses with no symbols in between, it's implied that there's multiplication. Okay, so this is just plugging in the numbers into the formula, right? Can we see that? Okay, well I just want to make sure we can do this one first, all right? We got to finish this first, all right? So when we do this, we get, are we able to punch this into our calculator? And we're getting this, 0.04053? Okay, so that's our standard error. So what is my z-score?
Z-score is
Okay, so with my null hypothesis, it says the number that I expect is 0. That goes in the middle. And what I'm observing is 0.08. Okay? That's my observed difference. So I want to know, do we have evidence, what's the probability of ending up in this part of the triangle? Okay? Or this part of the curve. So my z-score is going to be 0.08 minus what? Minus 0 divided by 0.04053. And what do I get? 1.97? Is that what we get? Okay, so I get 1.97. And with that, I look that up in my z table, and how much do I have in the tail? I get 0.0244. Okay. Depending on, I guess if you round it at 0.0405, you get 1.98 and you get 0.0239. But our answer is 0.0244. That is my p-value. Okay, do we have a question? 0.0244. Okay. So what is our conclusion? So let's assume alpha is 5%. So my p-value is less than alpha, which means what? We reject
we reject
the null hypothesis.
That this provides
And,
evidence.
okay, so if we reject the null hypothesis, we write this provides evidence that what?
That the new medicine
Is more effective.
is more effective.
Okay. That, yeah, the new medication is more effective than the old medication. I hope you guys have this all written in your notes, okay? Because the way this problem is set up is going to be very similar to how my quiz problems and final exam problems are set up, okay? You know, I was walking around and not everyone was even writing down the problem that I had written up on the board, okay? So I'm not sure what you guys are expecting, but But it goes both ways, okay? I'm doing my part, or I think I'm doing my part in providing you with the resources and tools you need. But you got to do your part in using them to study and learn, okay? And I know a lot of you guys are, but that cannot be said for all of you, I think. So, yeah. Okay, are there any questions on this? Yes?
You know what part I don't get when
Okay.
you wrote x equals 0.5?
X equals what?
Conclusion, under the conclusion.
Okay,
That's a five, that's not
so what part of the conclusion?
That's not an x? Not an x.
This is an alpha, okay? So alpha is 0.05. This is just an arbitrarily chosen value. Most commonly we choose 5%, okay? 0.05. But not always, okay? I might say use an alpha of something else, okay? Yes, question? Alright, keep it down, you guys.
So finding the z-score, it's the observed values, the standard error, that's all the whole.
It's the observed difference, yeah, over the standard error. Yes. Alright. Any other questions? No? Okay. Well, we're going to move on then and dig into chapter 9, which is pretty similar, except rather than dealing with proportions, we're dealing with the mean. Okay? So chapter 8 and all of this proportion business is for categorical variables, right? They improved symptoms, they did not improve symptoms. That's a categorical variable. In chapter 9, we're going to be dealing with numeric variables, okay? So we're going to do hypothesis testing and confidence intervals. Or numeric variables. Okay, so now we're dealing with numeric variables. So we're still dealing with samples, and based on the samples, we want to make a conclusion about the population. But this time, we're talking about a numeric variable. Okay, so we're still doing inference. Oops. Is using a sample Okay, so for example, what is well, just name a numeric variable that we might use.
Age.
Age. Okay, sure. What else can we use as a numeric variable?
Height.
Height,
Size.
weight. Sure, anything that we can measure as a numeric variable. So let's say we want to know what is the average height of an adult woman in the United States.
5'6".
5'7".
No,
Five, four.
girls.
5'5".
Okay, well, so all right, so there's some debate, okay, and we want to know, all right, okay, Are there people here, any adult women willing to share their heights with the class? Okay, sure. Okay, so let's. We will. This is now again.
Students as an adult.
Huh?
Are we all
You'll
adult
be
women,
the
or is there like a cutoff?
outlier.
No, we'll say you guys are all adult women.
Huh?
Five.
Yeah.
What? 5'2". You're not 5'2".
No, I saw growing in the 7th grade.
Okay, so let's say. All right, so we want to know what is the average height of an adult female in the U.S. Okay. Now, technically, this would not work because this, if we do a random sample, we do a sample here, it's not a random sample, right? Because I'm asking people who are volunteering their height, so that's not random, and plus it's just this classroom, so not random, okay? But let's pretend like these are values that we got from a random sample, okay? So we will say pretend random sample, which it's not, okay? But let's say it were, alright? Because when we check conditions, one of our conditions has to be that the sample is randomly obtained or independent from one another. Okay, so who said they're willing to volunteer? Okay, so how tall are you?
5'2".
5'2", okay. So we've got 5 foot 2 inches. Okay, who else?
5'5".
5'5".
5'4".
5'4".
5'7".
5'7".
5'1".
5'1".
5'8".
Okay, if I got 5'8". Well, who else?
Say it.
Another 5'7". What else? 5'6". Okay, I think this is plenty. 1, 2, 3, 4, 5, 6, 7, 8. Maybe we'll take 2 more for a nice 10. Yes.
5'3".
5'3" and 5'9". Okay. Okay. No, this is great. All right. So, based on this, what is let's use this. Okay. So here is our data, and we want to know what is the average height of a woman in the United States. Okay. So I'm going to convert all of these into inches total rather than feet and inches, right? Okay. So basically 5 feet is 60 inches. So I'm just adding 60 inches to all of the inch measurements. Okay. So I got 62, 65, 64, 67, 61, 68, 67, 66, 63, and 69. Okay? So this is my sample. Okay, now what does my sample mean? I add all of these up, and what do?
Divide them by.
Divide by 10, right? Okay, so somebody,
I'll do it.
you'll do that? Great. What happened to my own calculator?
65.2.
What is it?
65.2.
Oh my god.
All right. Well, let's just make sure. Let's have somebody else verify.
Wait, I thought you did it, so I was thinking last time.
Wait, did we all get 65.2? Do I have to verify this myself?
Yeah,
65.2. 65.2.
Yeah, I got 65.2. Okay. All right. So that's X bar. Okay. And can we do sample standard deviation? Is that too much work? Let's try this. Okay. I'll let me see if I can do this. Okay. Alright, so let me just let me do this really fast.
For the U.S.
said everything like that.
Oh.
That makes sense.
Okay, so and that's my sample standard deviation. Is this okay with everyone?
Yes.
Okay, so
No,
no?
you didn't count 5, 5, 3, and 5, 9 on the side.
I did.
Oh.
63 and 69. I'm sorry? These are my deviations, and then I squared the deviations and I added them up and divided by n minus 1, right? Huh? You guys learned this in like chapter 3, right? Calculating a standard deviation of a set of numbers.
This is what wasted my time on the midterm, and I didn't finish the last 2 questions. Very
Okay.
Okay, I apologize, alright? To calculate the standard deviation for a set of numbers, you find the mean, you subtract the mean from each number to get the deviations, you square the deviations, you add those up, divide by n minus 1, and I did that, and I got 2.6583, okay? So this is S, my sample standard deviation is 2.6583. Is this okay?
Yes, sir.
So I've got my sample mean and my sample standard deviation from a set of numbers, which is supposedly a random sample, okay? So based on this, what can we say about the population mean for the average height of an adult female, okay? So in this set, we're going to try to create a confidence interval, okay? So my confidence interval, do you guys remember what a confidence interval looked like for a proportion? So this is just review. This is not what it's going to be for the mean. Confidence interval for a proportion. What does that look like? For single proportion, in the middle I put in, I start off with P hat. P hat plus or minus what? Z star times standard error. Is that okay?
Yes.
All right. For confidence interval for mean, okay, it's very similar. P is the sample proportion. For a mean, what do you think I'm going to use? The sample mean, okay? Right? Confidence interval for proportion, I'm using the sample proportion in the middle. Confidence interval for mean, I'm going to use the sample mean in the middle. So what's the sample mean? X bar, right? Plus or minus. And for reasons that I will explain in a moment, instead of Z, we're going to use T, okay? Times my standard error, okay? So confidence interval for a mean, very similar, but instead of proportions, I'm using means, and then my Z becomes a T, and then the standard error, okay? Is this okay? All right, you guys. I don't know what's going on back there, but just keep the noise levels down here. All right. Standard error. What you're going to find is that the standard error, we're just formulas or equations that we're going to use. Some are uglier than others. In this case, the standard error is not too bad. It's S over the square root of n. Okay? S is your sample standard deviation. N is what?
The number.
Sample size, right? So in this case, my standard error is 2.6583 divided by the square root of 10. Is that okay?
Yes.
How did I do that in my calculator?
6583 divided by the square root of 10. I think you can just punch that in. And I'm getting, well, here's a good check for your calculator. I'm getting 0.8406.
06.
Yeah? No?
Yes.
Yes. Well, yes. This is, okay. Yeah, if you miss a number, that'll mess things up. Okay. So that's our standard error. X bar is what? 65.2. So we have 65.2 plus or minus t star times my standard error, which is 0.8406. Okay. All right. Who has their book with them? 5 of you. Okay. All right. To get your T stars, you're going to need your book. Okay. But a lot of you guys don't have your book, so we'll just do the best we can.
We go to the index?
Huh?
We go to the index?
Go to page A. What is it? A6? No, A7. Page A7 in the appendix. Okay.
Why are they both right?
Yeah, we only have right-tail probability. All right. You're going to have a table at the back of the book. If you have your book, share with a neighbor, please. And across the top, you have something that says confidence level. You guys can share. Okay. So across the top, you've got different confidence levels: 80%, 90%, 95%, etc., etc., etc. Okay. And then you've got a whole bunch of numbers under each column, okay?
Right.
What you want to find is you're going to have to pick something called degrees of freedom, okay? In our thing, degrees of freedom is equal to n minus 1. So how many degrees of freedom do I have? I have 9 degrees of freedom, okay? So I'm going to the row that says 9. Okay, for 9 degrees of freedom. And what level confidence do I want? Let's say I want a 95% confidence interval. Okay, so for a 95% confidence interval, I go to the column that says 95%, and I find the number that's in the row for 9 degrees of freedom. And what do I have, 2.262?
Yes.
2.262.
Wait, why 95% again?
That's just a number I picked, right?
Oh.
So, well, when we did confidence intervals for proportions, I would say make a 95% confidence interval or make a 90% confidence interval, right?
Right.
And you would use, 1.96 or 1.645 or something like that. Okay? So in this problem, I'm saying let's make a 95% confidence interval, and I'm going to use 9 degrees of freedom. So my T star is 2.262. Okay, is this okay with everyone? All right, so now I just plug that in. And so my confidence interval is 65.2 plus or minus 2.262 times 0.8406. And I get 1.90.
So we just plug it in.
Yeah.
And because
And that would be x bar?
Yeah, my n is 10, so I have n minus 1, 9 degrees of freedom.
That would be the x bar.
Huh?
That would be the x bar?
Well, I'm confused. What do you
No.
mean?
That's
Okay, so my confidence interval is 65.2 plus or minus 1.9. So I'm going to get two values, right? A high and a low. So I get 65.2 plus 1.9. And I get 67.1. And then I have 65.2 minus 1.9. And I get 63.3. (63.3) to 67.1. This is my confidence interval. Is this part so far okay?
Yeah.
Okay, so what is the sentence I write? My interpretation of the confidence interval.
I am 95%.
Okay, good, that's a good start. I am 95% confident that
The average height of an adult female in the US is between 63.3 inches and 67.1.
yeah, I'm 95% confident that the average height or the mean height of a female adult in the US is between
63.3 and
63.3 and 67.1 inches. Okay? Is that alright? So I say I'm 95% confident that the mean height of a female adult in the United States is between 63.3 and 67.1. So this is a statement about what?
Right.
what is the
About the mean height.
the mean height?
The mean height. And the mean height, we call that a blank of the population. A parameter. A parameter, right? Proportions only apply to categorical variables, okay? It's not a sample. It's a parameter, right? So we are making a statement about the parameter, which is the mean height of the population. And we say I'm 95% confident that the mean height of females in the US is between 63.3 and 67.1. Okay? This is not saying anything about individual females. It's not saying that if we pick a random female, there's a 95% chance that she's in here, okay? It's not saying that. We are only saying a statement about the average height of a female, right? That was the original question we had. What is the average height of an adult female in the US? Okay, and you guys gave me all sorts of answers. Well, based on our sample of 10...
5'3" and 5'7".
Huh? Yeah, 5'3" and 5'7", yes. Based on our random sample of 10, not random sample, but pretend random sample of 10 women from our own classroom, we have come to the conclusion that the average height, we're 95% confident that the average height is between basically 5'3.3 and 5'7.1. Does that sound reasonable? Yes, okay, and the true average height, well, we don't know the true average height, but based on much larger samples. So the United States does, there's a national health survey that they do, and they survey thousands of people. Their conclusion is it's about 5'4.5". Okay, that's their estimate for the average height in the U.S. Here we got something. Well, 5'4.5" is within our interval. Okay. All right, is that okay? This is okay with everyone? So this is making a confidence interval for a mean based on one sample. Okay? Confidence interval for a mean based on one sample. All right, based on my interval, let's say somebody said, let's say we asked that question and I said, what is the average height of a female in the U.S.? And someone said, I think the average height of a female in the U.S. is 5'8". Okay, so that's 68 inches. What would we say, do we say we have evidence for that or against that? Okay, we say we have evidence against that because what? Because 5'8" is not inside our confidence interval. Okay, is the camera?
Yeah, I don't know. I think I.
Okay, can you fix that? All right. So because 5'8" does not fall within our interval, we say we have evidence that the mean is not 5'8". Okay. If somebody says, I think the average height of a female in the U.S. is 5'4", what would we say? Do we say we have evidence for that, evidence against that? We don't have evidence, what?
Evidence for it. Between 6'3" and 6'7".
So someone says, I believe the average height of a female in the U.S. is 5'4". You would say, well, my interval is, I'm 95% confident that it's between 63.3 or 5'3" and 5'7", 67. And someone says that they're claiming it's 5'4". What would you say?
Well, it's between your intervals.
So you would say it's between my interval, and you would say we do not have evidence. We do not have evidence that it's not 5'4". Okay, which is a very different thing from saying we have evidence that it is 5'4". Can you guys hear the difference there?
Yeah.
Okay, so the claim is that the population mean. Do you remember the symbol for population mean? Mu is 64. Okay, that the population mean is 64. 64 is in my interval, but the thing I say is not. I do not say I have evidence that it is 64. All I can say is I don't have evidence that it's not 64. Okay?
I don't have.
I do not have evidence
That is not 64.
that it is not 64 inches. Okay? 64 inches is within my interval. Huh? So we do not say we have evidence that it is 64. Okay, don't say that. Yes.
Okay, if it says, I think someone says, I think the average height for women is 63.3, then we say we have evidence that, like, instead, do we say the same thing for that? I do not have evidence that it is not 63.3?
You're right.
Oh, you don't just say, like, I have evidence that it is 63.
No, any number within the interval, okay? So whether it's 65, 66, 67, 67.1, anything inside the interval, all you say is I do not have evidence that it's not that number, okay? Because we can't say that we know what the exact mean is, okay? All we can say is, yeah, that seems like a reasonable number. I can't confirm that's the number, but I can't deny that, okay? On the other hand, if somebody says, is it 63? 63 inches is outside of my interval, barely, but it is outside of my interval. Then you can say, I have evidence that it's not 63, okay? You can say you have evidence that it's not any number outside of the interval. Any number inside the interval, you can say,
I don't have evidence.
I don't have evidence that it's not that
It's
number.
not that number.
Okay. I know it's a little tough. Yes.
So we'll never say that something is true, but we'll argue for it?
Yeah, you will never gather evidence to say that a particular number is the number.
Right.
Okay. Right? Because it's all right. So I just made a claim that the average height of adult women in the United States is 5'4.5". Is that number true? Is that true though?
I have never.
Is the average height of adult women in the United States 5'4.5"?
I do not have evidence that.
Okay, well, what is the average height of adult women in the United States?
5'4.5".
No, it's something close to 5'4.5", right? If we took every single woman in the United States and we got their exact measurement, okay, and then there's whatever 150, 160 million women, or I don't know, adult women, maybe only 120 something million, I don't know. However many women there are, we take all of their heights and then we divide by 100 something million, okay? Am I gonna get 64.5 exactly?
No.
No.
No. I might get something pretty darn close to that, but I'm not gonna get 64.5 exactly. So my claim that the average height is 64.5 exactly is not a good claim,
Right,
okay?
right.
I can say I'm 90% confident that it's within, you know, an inch of 64.5 or something. I feel very confident about that, but we'll never actually, until we take the heights of all women in the United States and calculate the true average of all 100-something million people, we won't have the true average, okay? So we'll never have evidence that this one particular number is the exact number, okay? So that's why we always have to phrase things in this weird double negative state. Okay, how's that?
Right.
Is that okay? Alright. Alright, well let's take a break. I'll run to my office, grab some papers and such, and then